All right, we got an interesting function here, and in part A, we're being asked to simplify it to this much simpler function. So let's give that a go. Right, I'm going to start with the more complicated function, of course. And then we're going to have to use the addition formula to expand this. The question is, do we expand it and then multiply out the brackets, or multiply out the brackets and then expand it? Good question. I think I'm going to expand it first. So it's going to be 1 plus, now I'm just going to write up here, we've got cos A plus B is identical to cos A cos B minus sine A sine B. So we're going to get cos x cos pi over 4 minus sine x sine pi over 4. These are both 1 over root 2. And then I'm going to multiply by 1 plus, okay, we've got another addition formula. I can fit it in here. Sine A plus B is identical to sine A cos B plus sine B cos A. So in our case, it's going to be sine x cos pi over 4 plus sine pi over 4 cos x. And again, these are both 1 over root 2. I might, before I expand it out, I might just write it in a slightly simplified form because you've got to be really careful not to make a mistake. Right, now I've got this double bracket to multiply out. So I'll multiply each of the terms here by 1 first of all. And then I'll multiply each of the terms by, in the second bracket, by 1 over root 2 cos x. And this will become a half sine x cos x plus a half cos squared x. And then finally, this term with each minus a half sine squared x minus a half sine x cos x. So this cancels with this, and also that one cancels with that one. That's looking pretty good. If we just have a little sneaky look at the answer now, we've got 1 over root 2 plus cos x all squared. So collecting these up will give 1 plus 2 lots of root 2 cos x plus a half cos squared x. Now, if we look at the answer, there's no sine squared in there. So at this point, I'm going to replace. So, oh yeah, sorry, it's minus a half. I'm going to replace that sine squared by 1 minus cos squared. And now that, it's going to like focus on this bit. That is actually going to equal minus a half plus a half cos squared x. So I'm going to get 1 minus a half, that's a half, plus 2 over root 2 cos x plus cos squared x when I bring the half cos squared x and the half cos squared x together. And if we look at the answer, okay, we can see, I mean, you might not think immediately to factorize it like this, but given the answer, if you just sort of quickly multiply this out in your head, you can see that you're going to get the half, you're going to get the cos squared x, and you're going to get a crossover term, but you're going to get two of them. So this all checks out. And we've proven this result. Okay, good start. In B, we're asked to find the range of the function f of x, and of course it makes sense to look at this simpler form here. So it's a squared function, it can never be negative. We need to think about when it can be 0, or can it equal 0? And cos x can equal minus 1 over root 2. If we look at the graph, then we've got it's equal to 1 over root 2 at 45. So it's going to equal sorry, my graph's not that great, is it? It's going to equal minus 1 over root 2 at 118 minus 45. So 135, which we're working in radians, aren't we? I didn't do that. So it'd be pi minus pi over 4. It's going to be 3/4 pi. So f of x equals 0 when x equals, I'm just sort of proving that we can get, sorry, not when x equals that, when x is equal to 3 pi over 4. Just proving that we can get 0, basically. And then cos x will equal 1 when x is equal to, say, 0. So f of x will equal 1 over root 2 plus 1 squared, which we could expand this out. We're going to get a half plus 1 plus 2 over root 2, or 3 over 2 plus 2 over root 2 when x is equal to 0. And therefore the range is going to be f of x. It depends what notation we want to use. We could use interval notation here. So it's going to be 0 to 3 over 2. Just got to move that along a little bit. 3 over 2 plus, actually this thing here is root 2. Or, of course, you could write it as an inequality. That's fine as well. In figure 2, we're given a graph of y equals f of x, and we're then asked to find the coordinates of all the maximum and minimum points on the curve. So we've just identified the range, in fact, and we had that it was between 0. We also, I'm just going to jump straight to it. Remember, we said it was 0 when x was 3 pi over 4. Where's it gone? But it is worth also thinking of where else it's 0, and it would also be 0. Let's just look at it. It's going to be, so we've got pi here, so it's going to be pi plus pi over 4, which is 5 pi over 4. So we've got minima at 3 pi over 4, 0, and 5 pi over 4, 0. Then we've got global maxima at, now I talked about 0 before, so it's going to be 0, and then it was 3 over 2 plus root 2. But another place where we would have got this maximum would have been at 2 pi. If we just look back up here, it was when, sorry, so I'm going to put this in as, yeah, 2 pi. That also gives cos x is equal to 1. The graph obviously helps us see this. And that just leaves one point to find, and it's here. We have a local maximum. Now, I feel just by looking at the function and the equation, we can see that it is symmetrical. It's got to be that this point here is going to be pi. And then we just need to substitute pi into this. And we're going to get 1 over root 2. Now remember, cos looks like this. It's actually minus 1 when x is pi, which will give a half plus 1 minus 2 over root 2. So it's going to be 3 over 2, 3 over 2 minus root 2. If you want to be really careful, and actually the mark scheme does this, then you could differentiate the function, and you'll see that that there is a solution when x is equal to pi. I'm just going to write using symmetry. I feel that's justified. So there we have it. These are all our maximum, maxima, and minima. Finally, we have part D. So the curve, we've drawn a line across at y equals 2, and we've got a region bounded by this line and the curve. We're asked to find the area of R. I'm going to need to be able to find these values here. So I'll call them A and B. And to do that, we'll solve the function, which is 1 over root 2 plus cos x all squared is equal to 2. That's where they're going to intersect. We can square root both sides. And then minus this, well, actually, we can actually write it as minus 2 over root 2 or 2 over root 2. That will be easier to then deal with. So cos x will equal minus 3 over root 2 or 1 over root 2. Note that this one is less than 1, so we'll reject it. X is going to be pi over 4 as one solution, or if the other one's going to be over here, so it's going to be 7 pi over 4. I can add these on now. I've got a rectangle then with height 2 and base is going to be 6 pi over 4, which is equivalent to 3 pi over 2. And so the area of the rectangle is going to be 3 pi. And the area of R is therefore going to equal 3 pi minus the integral. I'm just going to write f of x between pi over 4 and 7 pi over 4. So that's what we've got to figure out. I might just do it without the limits to start with. Another thing we could do actually is we could use this line of symmetry and we could just integrate from pi to pi over 4 and then double it. It doesn't seem a massive advantage in this case other than the fact that pi is a little bit easier to substitute into integrals. I think I'll go with it, to be fair, but 7 pi over 4 should be fine as well. Using little things like this can often just help a little bit. So we need to find the integral, and like I can't remember if I said this already. I'm just gonna not worry about the limits for the moment because I think the integrals, it might be complicated. 1 over root 2 plus cos x all squared dx. Now, it is possible to expand this out, get a cos squared, use double angle formulae. It won't be too bad. You can deal with the constant, you can deal with the cos x term. The way I did it, I'd like to share, is actually I returned to the very start of the question where we were given the function equal to this. And if I now expand this out, but I don't use my addition formulae, then I'm going to get 1 plus sine x plus pi over 4 plus cos x plus pi over 4 plus cos x plus pi over 4 multiplied by sine x plus pi over 4. And actually, this is really nice. The only slight issue is this term here. But remember, we have that sine 2a is equal to 2 sine a cos a, and therefore this term here, I could divide by 2 to give this, and therefore if my a is x plus pi over 4, this is going to equal a half sine 2x plus pi over 2. I've just doubled both. Then the integral is going to be x. Sorry, I don't know why I've left the integral sign in there. X minus cos x plus pi over 4 plus sine x plus pi over 4 minus a quarter cos 2x plus pi over 2, plus c technically. Therefore, the area of R will equal that 3 pi that we had minus 2 lots. Just going to remind you where this came from here. So I've worked out the integral without the limits, but now I've got 2 lots of it with the limits pi over 4 and pi. Okay, here goes. Going to still have this 3 pi. Then I'm going to substitute in for pi. Here I'm going to get 2 pi plus pi over 2. Remember, cos is periodic about pi, about 2 pi. So this is just going to become cos pi over 2. And then I need to minus. I'm going to take care of the minuses as I go along. So minus pi over 4 plus cos pi over 2. So I've got a double negative, and pi over 4 plus pi over 4 is pi over 2. Minus sine pi over 2 plus a quarter cos. It's going to be 2 times pi over 4, that's pi over 2, plus pi over 2 cos pi. And that's all in the bracket. Okay. I did say this was a little bit easier. Well, I implied that, didn't I? This is, I guess, I don't know. I don't have to deal with double angle formulae, but I get all these sort of transformed cos and sine functions instead to deal with. So let's draw the graphs of sine and cos to help us. First of all, I can combine the pi and the minus pi over 4, so that's going to become 3 pi over 4. So I've dealt with this and this. Then I'm going to minus cos of 5 pi over 4. Remember, cos of pi over 4 is 1 over root 2. This is going to become minus 1 over root 2. So it's going to be minus 1 over root 2, so plus 1 over root 2. But sine 5 pi over 4 will be minus 1 over root 2. So those will cancel. And then I'm minusing 1/4 cos pi over 2, but that is actually just equal to 0. And the same over here, in fact. The minus sine pi over 2 will be minus 1. And then cos of pi is equal to minus 1. So this will give me minus 1/4. Very easy to make mistakes, I think, but let's hope I haven't. So it's going to be 3 pi minus 3 pi over 2. This here is going to equal minus 5 over 4. So I'm then going to be adding minus 2 times minus 5 over 4. That's going to be plus 5 over 2. And finally, this is actually 6 pi over 2. So 6 pi over 2 minus 3 pi over 2, that's 3 pi over 2 plus 5 over 2. And that is the area of our shaded region R. If you did double angle formula, it would have worked out in a similar sort of way. I'm not going to go through that. I think the mark scheme does that. Quite a nice approach, this one, I think. At the end of it, that's what you're trying to get. Okay, well done if you did. Well done on your efforts. Keep going.